In this video, which is part 2 of the quantum machine learning series, we will once again enter the quantum world and build a variational quantum classifier together. This series is designed to provide not only an introduction to quantum machine learning, but also a third step into quantum computing in general. The guiding idea is that we take a classical problem, in our case the XOR problem, from machine learning and translate it into the quantum world. In part 1, I already explained the basics of machine learning and presented the problem in a way that was hopefully clear and complete. We also simulated it together in code, and now in this video the focus will be on bringing this classical problem into the quantum setting. For an overview of what this video covers and how we'll proceed, step by step, first I'll explain how a variational quantum classifier, a VQC, works in general. That is, I give a high-level overview of the VQC workflow. Then I go through the individual steps and explain the theory wherever necessary. Simpler steps I'll address briefly when we get to the code, while the quantum-specific and important parts I'll explain theoretically beforehand. Once we have the full theory and a clear understanding of how a VQC works, we'll write code using Qiskit libraries to simulate the whole setup. And after that, we'll run it on a simulator. How does a variational quantum classifier works in general? Why do we even call it a variational quantum classifier? The quantum part should be clear. The whole model works with qubits and quantum mechanics, hence quantum. The term classifier comes directly from classical machine learning. We have certain inputs and we want to assign them to certain outputs. In the XOR problem, for example, the inputs 0, 0 and 1, 1 should be mapped to class 0, while 0, 1 and 1, 0 should map to class 1. What we are doing here is a classification task, so the model is called a classifier. The term variational originally comes from the variational principle in physics, or more generally from mathematics. You don't need to know the details here, but the core idea is that we optimize something. In our case, we optimize the parameters of a quantum circuit by iteration. Just like in classical machine learning, we adjust the parameters based on the output until we get the results we want. That's why it is called variational. So how does the structure look in practice? Let me give a short overview before we dive into the details. We start with classical data, which must be encoded into the quantum world, into quantum states. This step is called data encoding. The name is quite intuitive. We encode classical data into qubits. In quantum machine learning, this process is also often referred to as a feature map. I'll explain in more detail in a moment what exactly happens here and what you need to know. Next, we construct our quantum neural network, which we call the variational ansatz. Here we define the structure of the network, the foundation that makes learning possible in the first place. After that, we need to specify how the measurements are performed and which observables we define in order to extract information from our quantum system. Finally, we perform the actual training of our variational quantum neural network. Before I go into the feature map, I'd like to briefly repeat what a qubit is and what the Bloch sphere has to do with it. A qubit, in principle, can be any physical system that we can use in a quantum mechanical way. Specifically, one that allows us to create superpositions and to create entanglement with other systems. These two properties are really the foundation of what makes a qubit useful. No matter what physical platform we use, a system has to be able to do these things in order to serve as a qubit. To make this more concrete, I think photonics provides a very intuitive example. In photonics, we work with photons, particles of light. Imagine we have two optical rails or waveguides and a source that emits single photons. If we initialize the photon in the first rail, we call that state 0. If we initialize it in the second rail, we call that state 1. That's the simplest possible encoding. But we can go further. With a beam splitter, we can create a probability distribution for a photon between the two rails. Suppose we send the photon into a beam splitter that directs it with 30% probability into the first rail and 70% into the second. If we repeated the experiment 100 times, we would detect the photon about 30 times in rail 1 and 70 times in rail 2. What does this mean? It means that the photon is not simply in state 0 or 1, but in a superposition of both states at once, until we actually measure it. This superposition gives us far more possibilities than just two basic states. Instead of being limited to 0 and 1, we can create many different states by varying the probability distribution. For example, we could encode not just two values, but in principle a whole range, say the numbers from 1 to 100, each corresponding to a different superposition between 0 and 1. A beam splitter can be imagined as a half-mirrored piece of glass. If we looked at it in real life, part of the light would simply be reflected and part of it would pass through. Think of a normal glass window. Almost all of the light goes through, but a small part is reflected. You can see your own reflection in the glass. Now, with light at the single photon level, the effect is the same. Part of the light is transmitted, part is reflected. But here's the key point. A photon cannot be split in half. It's not that half of the photon goes through and the other half is reflected. Instead, the photon behaves probabilistically. When we measure it, the photon will be detected either in the transmitted path or in the reflected path, with a certain probability for each outcome. And that's exactly how a beam splitter works at the quantum level. It gives us these probabilities of reflection and transmission. And the way we visualize all of these possibilities is with the Bloch sphere. Every point on the surface of the Bloch sphere corresponds to a possible quantum state of a single qubit. There are hundreds of videos about the Bloch sphere on the internet, but I'll try to keep it in short here and explain it in a simple and intuitive way. As you can see here on the right, we have the Bloch sphere, and on the left we see interference. I'll come back to that in a moment. Let's now build up the concept of why we use this Bloch sphere in the first place. Above we see alpha times the 0 state plus beta times the 1 state. This is our quantum state. This state is what we represent on the Bloch sphere. Alpha and beta don't just tell us the probability distribution, that is how likely we are to measure 0 or 1, they also give us information about a second property, the so-called phase. So what is the phase? The phase is a property of waves, and it's important to consider, especially when we are dealing with multiple waves. To understand this, imagine two waves. In the bottom left part of the image, you see two such waves. The lower two curves that are not very tall. These waves are exactly the same. They have the same period, the same amplitude, and they are perfectly aligned, meaning they are in phase. If these two waves meet, like Waller waves, they would clearly amplify each other. If we simply add them together, each wave peak adds to a peak, and each valley adds to a valley, the result is the wave above them, which has double the amplitude. However, if the two waves are shifted, if the peak of one wave aligns with the valley of the other, then they would completely cancel out. If we add them in that case, they interfere destructively and the result is 0. That's why on the right we only see a red flat line. No wave remains. This shift between the waves is what we call a phase difference. So the phase describes how much one wave is shifted relative to the other. And that's crucial because when waves interfere, the result depends on this phase. In the first case, the phase difference is 0 and they amplify each other. In the second case, the phase difference is 180 degrees and they cancel each other out. That's what phase means. This same property, phase, also exists in quantum states. It becomes relevant when, for example, we apply a second beam splitter to a quantum state. The resulting outcome depends not only on the probability amplitudes, but also on the relative phase. The states interfere just like waves, and depending on the phase, the output will change. You don't have to fully visualize why that happens, but it's a fact, and that's why we must encode this phase in our representation. Now, as we've said before, we represent our quantum state using vectors. Why? Because linear algebra gives us a powerful mathematical toolkit. It's practical and widely used in quantum mechanics, so we'll just go with it. It's important to understand the vector that represents the quantum state must have a length, or more precisely a norm, equal to 1. That's because this norm corresponds to the total probability of the state, and the total probability must always be 1. The photon must either be in state 0 or in state 1. It can't just disappear. So to summarize, we represent our quantum state as a vector. This vector encodes all the information of the state, and its length must always be 1. That's our first requirement. So how can we do this? Let's try it first in 2 dimensions. Imagine a 2D coordinate system with 2 axes. We could use a circle with radius 1. Every point on this circle would then represent a vector of length 1. But here's the problem. If we say the vertical axis represents the probability distribution and the horizontal axis represents the phase, then we can only assign 2 possible phase values to each probability distribution. One to the left and one to the right. But in reality, for every probability distribution, we can have an infinite number of phase values. So this 2D model is too limited. So what can we do instead? Here comes the elegant trick. We move it into 3D space and replace the circle with a sphere. More precisely, the surface of a sphere with radius 1. This allows us to still enforce that every vector has length 1, because we stay on the sphere's surface. But now we have 2 degrees of freedom. What we do is this. We move vertically along the sphere to represent the probability distribution. That's like moving up or down along the z-axis. This angle is called theta. Then we rotate around the sphere. That's our second angle, phi, and this represents the phase. Together, these 2 angles uniquely determine a point on the sphere's surface. And since the sphere has radius 1, every vector has length 1. That's why we use the Bloch sphere. Every point on its surface corresponds to a valid quantum state, with a fixed total probability, a defined distribution between 0 and 1, and a phase. And all of this can be visualized with just 2 angles, theta and phi. It's an elegant and practical way to represent everything we need to describe a single qubit. What we do in the feature map, or in data encoding, is the following. We start with our classical data, in our case input 1 and input 2, each of which can be either 0 or 1. And now we need to bring these data into our qubits. This is actually very simple. We just say if the input is 0, then the qubit should be in state 0. And if the input is 1, then the qubit should be in state 1. This is called basis encoding, the simplest way of encoding data, and it's designed for binary tasks. Since we have 2 inputs that can each be 0 or 1, we also use 2 qubits. Each qubit represents 1 input, so each qubit can be in state 0 or 1. That means we will initialize 2 qubits and then apply a gate that puts the qubit into the correct state on the Bloch sphere, either in state 0 or in state 1. And that's exactly what a feature map does. For our example, this is relatively straightforward, because we only need to encode binary values, 0 and 1. But if we wanted to encode real numbers, like in image recognition tasks in machine learning, where pixels values are real numbers between 0 and 1, then we would need more than just 2 points on the Bloch sphere. We would need to use the entire surface of the Bloch sphere. For that, there are other encoding methods. For example, angle encoding or amplitude encoding. All of these methods do essentially the same thing. They assign a classical value to a specific point on the surface of the Bloch sphere. They just differ in how exactly they do this. And depending on the application, one encoding might be more advantageous than another. For example, more resource efficient. But in our case, we only need basis encoding. We just want to encode 0 and 1, not real numbers. So our job is very simple. And that's exactly what we'll implement in the code. That's the purpose of the feature map or data encoding. Now let's move on to the variational ansatz. First, let's clarify the term. Why ansatz? By ansatz, we simply mean the structure of our quantum circuit, the layout we fix in advance. And variational because the circuit contains parameters, just like in classical machine learning, that we vary during training. Hence, variational ansatz. So what does this circuit look like? I'll first walk through the pieces at a high level and then go into the details step by step. As we already know from the feature map, we have 2 inputs and therefore 2 qubits. That means we have 2 qubits we can manipulate. How do we manipulate them? First, we apply an RY gate to each qubit. I'll explain in a moment what an RY gate is and why we use it. Next, we apply a C0 gate to create entanglement. I'll also briefly recap what exactly it does. Next, we apply a second RY gate to qubit 0 only. We don't apply another RY gate to the second qubit, just to the first one, qubit 0. And finally, we measure only qubit 0. That measurement provides the model's output. 0 if the input was 0, 0 or 1, 1, so equal bits, and 1 if the input was 0, 1 or 1, 0, so unequal bits. In other words, the label comes directly from measuring qubit 0. In fact, if you take a close look at the truth table we are using, where the output is 0 for equal inputs, 0, 0 and 1, 1, and 1 for unequal inputs, 0, 1 and 1, 0, you'll notice that this is exactly what a C0 gate produces. The way a C0 gate works is simple. If qubit 0 is 0, nothing happens. Qubit 1 stays the same. But if qubit 0 is 1, then qubit 1 gets flipped. This logic perfectly matches the XOR behavior we want. So yes, measuring qubit 1 directly after the C0 gate would already give us the correct output. At this point you might wonder, why don't we just measure qubit 1? But in this setup, our goal is not to hard-code the solution. Instead, we want to show how a trainable quantum model can learn to approximate a target function, in this case XOR. That's why we deliberately avoid measuring qubit 1. We use the C0 gate here not to directly produce the XOR result, but rather to create entanglement between the qubits. The model must learn to extract the correct output by adjusting the parameters of the RY gates. So the design is intentional. We're building a learnable quantum circuit, not a fixed logic gate. Now let's explain why we use exactly 3 RY gates and why we need entanglement via a C0. I start with the C0. I've just explained how a C0 gate works, specifically when qubit 1 gets flipped and when it doesn't. This is what creates entanglement. If qubit 0 is put into a superposition and we then apply a C0, qubit 0 is simultaneously 0 and 1. Consequently, the target qubit, qubit 1, is both flipped and not flipped at the same time, so it must also end up in a superposition. At that point, the 2 qubits can no longer be treated independently, they share a joint state. And that's entanglement. This also explains why we need an RY gate on qubit 0 at the beginning. RY rotates the state vector of qubit 0 about the y-axis on the Bloch sphere. Starting from state 0, that creates the superposition we need so that C0 can actually entangle the qubits. Without putting qubit 0 into superposition first, C0 would not create real entanglement. As we can see here on this website, which you can access through the link I'll also put in the video description, we can illustrate this concept a bit more clearly. Here we have the Bloch sphere showing the x-axis, the y-axis and the z-axis, and the state vector 0 and the state vector 1. On the right, we can choose how we want to rotate the qubit. What the RY gate does is rotate the state vector around the y-axis. That means the vector turns exactly as I showed earlier in my drawing. For example, if I set it to +90 here, we can see that from this perspective, the vector rotates about 90 degrees to the left. If I then add another plus 90, we reach the state vector 1. And another plus 90 and another plus 90. And we're back at the starting point. So this should help make it clearer what the RY gate actually does. It simply rotates the state vector along this blue circle and nothing else. Why do we also apply an RY gate on qubit 1? At first glance, this is not obvious, but it becomes crucial once we look at the bigger picture. What we ultimately want is an entangled state that has amplitude on all 4 basis states: 0, 0, 0, 1, 1, 0, and 1, 1. In other words, we want a state in which all of these outcomes are possible when we measure. If we rotate only qubit 0 with an RY gate and leave qubit 1 untouched in its initial state, we don't achieve this. For example, suppose qubit 0 is placed into a balanced superposition, that is equal probability for 0 and 1, which corresponds to the x-axis on the Bloch sphere. Meanwhile, qubit 1 remains in 0. Before applying the C0, this gives us a state with equal weight on 0, 0 and 1, 0. These two components are not yet entangled, but after the C0, they evolve into 0, 0 and 1, 1. The result is the familiar Bell state 0, 0 plus 1, 1 divided by the square root of 2. This is indeed an entangled state, but it only covers 2 of the 4 basis states. And that is not what we want. We need all 4 basis states to be present in order to build the classifier properly. For that reason, we don't just rotate qubit 0 into superposition, we also rotate qubit 1 with an RY gate. Only then do we enter the full 4-dimensional space with amplitudes on 0, 0, 0, 1, 1, 0 and 1, 1, rather than being restricted to just 2 of them. So the logic is, RY on qubit 0 puts it into superposition so that C0 can entangle. And RY on qubit 1 ensures the entanglement covers all 4 basis states, not just a subset. Next step, we apply another RY gate, but this time only to qubit 0. Let me explain what this step does and how we should think about it. To do that, I need to briefly restate our goal. Our inputs are the 4 bit strings 0, 0, 0, 1, 1, 0 and 1, 1. These are what we use to initialize our 2 qubits. What we want is the following. If the input is 0, 0 or 1, 1, the output should be 0. And if the input is 0, 1 or 1, 0, the output should be 1. How do we get there? Later, I'll go into more detail, but the key idea is this. Eventually, we will measure qubit 0. A qubit can be measured in different bases. Here, we'll measure in the C basis. That means our measurement has 2 possible outcomes. If qubit 0 collapses to the state 0, we record the result as +1. If qubit 0 collapses to the state 1, we record the result as -1. This convention, +1 for 0 and -1 for 1, is standard and sufficient for us here. Now what we want is to set up the system so that for input 0, 0 or 1, 1, qubit 0 ends up in a state 1, so the measurement result is equal to -1, and for input 0, 1 and 1, 0, the qubit 0 ends up in a state 0, so the measurement result is +1. Later, during training, the model will adjust its parameters so that this mapping is learned. How do we achieve this? After the entanglement step, our joint 2-qubit system lives in a 4-dimensional Hilbert space, spanned by the basis states 0, 0, 0, 1, 1, 0 and 1, 1. The state vector can collapse into any one of these basis states upon measurement. What we now do with the final RY on qubit 0 is tilt the vector in this 4D space so that when the input is 0, 0 or 1, 1, the state vector collapses with either 100% probability into either 0, 1 or 1, 1, And in both of these, qubit 0 is in state 1, so measurement yields -1. When the input is 0, 1 or 1, 0, the state vector collapses with ideally 100% probability into either 0, 0 or 1, 0. In both of these, qubit 0 is in state 0, so measurement yields +1. In other words, that final ROI gate on qubit 0 acts like the decision boundary. It orients the joint 2-qubit state so that the measurement outcome on qubit 0 matches exactly the XOR pattern we want. Equal inputs give one class and unequal inputs give the other. I'd now like to try to illustrate this idea. What we see here is again the Bloch sphere in 3 dimensions. Of course, this does not represent the full reality, because in reality we are working in a 4-dimensional space. I cannot draw that here, but for the sake of illustration, we'll use this simplified picture. So let's imagine the 3-dimensional Bloch sphere as if it were embedded in 4 dimensions. We'll just assume that for now, even though we cannot visualize it. On this sphere, I've marked the 4 state vectors. Previously, we had the state 0 at the North Pole and the state 1 at the South Pole. Now, in analogy, we can think of the 4 2-qubit basis states 0, 0 at the North Pole, 1, 1 at the South Pole, 1, 0 on the x-axis and 0, 1 on the y-axis. Again, this is not the literal geometry, but it serves as a visualization. Now consider our state vector. What the RY gate does is rotate this vector in the 4-dimensional space to a new position. And here's the idea. With the first 2 parameters, the qubits are rotated around the y-axis, then entangled with the C0, and we enter the 4-dimensional joint space. At this stage, depending on whether the input is 0, 0, 1, 1, 0, 1 or 1, 0, our state vector points to some location in this 4-dimensional space. Now the role of the final parameter, the last RY gate on the qubit 0, is to rotate this vector once more in such a way that if the input was 0, 0 or 1, 1, then the state collapses with 100% probability into either 0, 1 or 1, 1, and essentially 0 probability into 0, 0 or 1, 0. And accordingly, for the inputs 1, 0 and 0, 1, the state should collapse into the other 2 outcomes. So here in green, I'm showing an example of what that state vector might look like. Just an illustration, of course it's not exact. If the input is 0, 0 or 1, 1, the vector might point somewhere over here, so that it collapses with high probability into these outcomes. And if the input is 0, 1 or 1, 0, then it might point over here instead, so that it collapses into the opposite result with high probability. Of course, in reality this happens in a 4-dimensional space, so the actual picture is a bit different, but this is just to build intuition. So this is, in essence, how our variational ansatz works. First, an RY gate on each qubit, then the C0 gate for entanglement, then another RY gate on qubit 0, and then the measurement of qubit 0. Notice that we don't care what value qubit 1 takes. Whether it's 0 or 1 makes no difference, because we never measure it. From the perspective of our classifier, states 0, 1 and 1, 1 are equivalent. They both mean output 1. Similarly, 0, 0 and 1, 0 both mean output 0. This explains why we do not apply another RY gate on qubit 1 after the entanglement. A rotation on qubit 1 would only change the balance between its 0 and 1 components. But since we never measure qubit 1, that parameter would have no effect on the training objective. The optimizer would never adjust it because it provides no useful information for the classification. And that's why our ansatz has exactly 3 parameters, and why it works for XOR. Now let's move on to a short explanation of measurement and what an observable actually is. An observable, in simple terms, is just what we measure in reality. For example, going back to our photonics analogy with 2 rails, so 2 optical waveguides, we can ask, is the photon in rail 1 or in rail 2? Rail 1 corresponds to state 0 and rail 2 corresponds to state 1. If we simply measure where the photon is, that measurement itself defines our observable. Another observable could be the phase between the two paths. In photonics, we could realize that by adding a second beam splitter and then again detecting which rail the photon ends up in. That way, the interference tells us something about the relative phase. That too is an observable. From the mathematical perspective, an observable is a matrix, and the eigenvalues of this matrix are the possible measurement outcomes. I won't go deeper into the mathematics here, but that's the essential point we need. An observable corresponds to what information we obtain from the measurement. So for our case, the observable we use is the Pauli C operator. This means we're simply measuring, is the photon in rail 0 or in rail 1. In practice, that's all we do, detect which rail the photon is in. Let me briefly add what it means if we measure in a different basis, say the Pauli X basis. In that case, we are measuring along the x-axis of the Bloch sphere. As I explained earlier with the photonics analogy, we have a photon source followed by two rails. A beam splitter corresponds to a Hadamard gate, which puts the photon into a superposition. Now suppose we have a perfect superposition. That is 1 divided by the square root of 2 times the 0 state plus the 1 state, the so-called plus state. If we then apply another beam splitter, meaning another Hadamard gate, we are effectively measuring in the x basis. The result is straightforward. If the state was in the plus state, the photon will always be detected in rail 0. If the state was in the 0 state, the photon will always be detected in rail 1. So just like with the C basis, the outcome is still either one detector or the other. But now the interpretation is different. Rail 0 corresponds to the plus state and rail 1 corresponds to the minus state, just like I've drawn it here on the Bloch sphere. Let me briefly walk through the training loop. First, we build a quantum circuit. Then we define the observable, that is the basis in which we measure qubit 0. Next, we compute the expectation value. Intuitively, this is what you would get if you repeated the C basis measurement on qubit 0 a very large number of times and averaged the outcomes. If every shot yields plus 1, the expectation is plus 1. If every shot yields minus 1, the expectation is minus 1. If the outcomes are split 50-50, for example, the expectation is 0. So the expectation value is simply the average over many measurements. We then use that expectation value to compute the loss. From the loss we compute the gradient. And this is where the actual training happens. We update the circuit parameters in the direction indicated by the gradient. We repeat this, compute, expectation value, loss, gradient, update, until the loss is small enough and the model reaches an acceptable result. So that's the end of the theory we need. Now I switch to the coding part, write the full implementation and fill in any details I skipped over here.